Discrete random variables are represented by specific points on a number line, and they typically consist of a set of whole numbers or integers that are countable, like test scores or the number of males and females in a class. By contrast, continuous random variables include the partial values between integers which may be rational or irrational real numbers. The domain is often restricted for real-world problems to make sense. For example, the heights of females in a classroom. A realistic range of heights will be restricted between, say, if they're 17 years old, 100 centimeters and 200 centimeters, for example. Continuous random variables are usually measured like time, distance, temperature, heights, and the probability of a certain outcome associated with the continuous random measurable variable is explained using the following example. Now I'm going to use an example to explain the probability of a certain outcome because continuous random variables on a number line include the entire number line. So in the previous example, x was equal to 0, 1, 2, 3, and 4, and there was a probability associated with the outcome of x equaling 0, 1, 2, 3, or 4, and the sum of those probabilities equaled 1. But on a continuous number line, x can equal any number in between 1, 2, 3, or 4. So it can have any value on that number line. And you want to measure the probability that x equals a specific value on a continuous number line. The sum of the probabilities will still equal 1 between x equals 0 and 4. But how you calculate the probability of x having a specific value for a continuous random variable is different than for a discrete random variable. Let's consider an example of a continuous random variable. Think about an AFL game. The time that the AFL player spends on the ground during a match in minutes could be represented by the continuous random variable t. Now, it's not possible for a player to spend negative time on the ground during an AFL match. And it's also not possible for an AFL player to spend more than 150 minutes on the ground during an AFL match. So that's an example of the restricted domain for the continuous random variable t that was spoken about before. So t will be less than or equal to 150 or greater than or equal to 0. Anyone who understands AFL knows the player is more likely to spend 80 minutes on the ground per game than 140 minutes on the ground per game. However, the probability of t equaling 80 minutes compared to the probability of t equaling 140 minutes is 0. Pause the video and take a minute to think about why that is the case. It's easy to explain if we consider the continuous random variable on a number line. So if this is the number line representing time t, the probability of t equaling 140 minutes and the probability of t equaling 0 is here. And I'll define a function f of t, and f of t is what we call a probability density function, which represents the probability that a player will be on the field within a time frame. I'll explain that in more detail. If we consider the possible times that a player can be on the field during an AFL match, starting from 0 and going to, say, 150. Put 150 here. And I make it the number line very dark, between 0 and 150. These are all the possible times that a player might be on the field during an AFL game. But the probability that this specific time at t equals 140 equals the probability of this specific time of t equaling 0. Think about it when you consider the accuracy in time, calculated time for the playing time of the player on the field, past the decimal place. What you're really saying here is the probability that t will equal 0.00000000 compared to the probability that t will equal 140 point, how many zeros did I have? 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9 equals 0. And you're comparing the probability of both of those outcomes occurring. And look at the accuracy to the 9th decimal place. So if you consider all the possible outcomes to the 9th decimal place and beyond, what is the probability of t equaling that specific number? It's very slim, because that's one outcome over the total possible infinite number of outcomes between 0 and 150. And that is why the probability equals 0. Because there are an infinite number of possible outcomes between 0 and 150, and you are asked to determine the probability that an exact outcome will result on that real number line. What makes more sense? It makes more sense to talk about a range of outcomes. So what is the probability that t might equal between 130 minutes and 150 minutes? Or what is the probability that the playing time will be between 50 minutes and 90 minutes? So what's the probability that the playing time will be between this range? Well, this range, this is a proportion of the larger range, a measurable proportion of the larger range. And it's more easy to determine using something called a probability density function. The probability density function is defined by f of t. So f of t represents the probability density function associated with the time an AFL player might spend on the ground per match, and the probability that the player might spend between 50 and 90 minutes on the ground would be given by the area under the probability density function. Applying the mathematics that you have learned in calculus, pause the video and think, how might you calculate the area under the probability density function over the interval t between 50 and 90 minutes? The answer is you would integrate. The definite integral of f of t between 90 and 50 minutes is the probability the AFL player would spend between 50 and 90 minutes on the ground during an AFL match. And you could calculate any probability within that restricted domain between 0 and 150 minutes that a player might spend on the ground during that AFL match, using the probability density function. Consider the probability density function f of x equals 1 over x squared. If we graph that probability density function, it will look something like this. And in the question, we're given a restricted domain. Calculate the probability that x will fall between 1 and 2. In other words, what is the area under this curve? The probability that x will fall between 1 and 2 is the area under the probability density function over that restricted domain, which equals the integral, the definite integral, from 2 to 1 of x to the negative 2 dx. So I just rewrote f of x in terms of a negative power. That will be negative x to the negative 1 evaluated from x equals 2 to x equals 1, which is negative 1 over 2 minus negative 1 over 1, which equals negative 1/2 plus 1, which equals 1/2, or 50%. So the probability that the random variable x will fall between 2 and 1 is 50%. It's worth noting at this point that the probability that x is greater than 1 and less than 2 equals the probability that x is greater than or equal to 1 and less than or equal to 2 because of the continuous random variable and the fact that the probability of an exact number occurring is 0, as discussed in the previous section.